Okay, so in this video, I would like to review the contents we had back in chapter 9. So this is a review session for your upcoming exam 2. And in this video, I'm reviewing the gas power cycle. Now, we had at the very beginning of chapter 9, we had a couple of definitions. The first thing we had was the air standard assumption. And there are 4 assumptions into air standard assumption. The first assumption says that the working fluid is air, which behaves as an ideal gas. Okay, so the working fluid is continuously circulating in a closed loop, and according to the air standard assumption, is behaving or is assumed to behave as an ideal gas. So this WF is working fluid. The second assumption we had under air standard assumption said that all processes are internally reversible. Okay, so all processes are internally reversible. So that means under the air standard assumption, there is no irreversibility, there is no friction. The idea behind air standard assumption is to make the calculation or analysis of gas power cycles easier. The third assumption under the air standard assumption says the combustion can be replaced by a heat addition process. Okay, so instead of discussing about combustion, we can discuss about heat addition, or we can assume or consider an heat addition process. So combustion is replaced by. So again, the third assumption under the air standard assumption says that the combustion is replaced by the heat addition process. The reason that we do that is the topic of combustion itself is a pretty sophisticated and complex discussion and topic. So we don't want to add the complexity of combustion and those chemical reactions into the discussion of the gas power cycle. And finally, the last assumption under the air standard assumption says that the exhaust process can be replaced by a heat rejection process. So 3 and 4 are opposite to each other. So the exhaust process can be replaced by a heat rejection process. Okay, so instead of discussing about the exhaust, we just consider that as a heat rejection. Now, these 4 make the air standard assumption. In addition to air standard assumption, we may have in problems, we may have cold air standard assumption. All right, cold air standard assumption. And the cold air standard assumption has 1 to 4 in the air standard assumption. In air standard assumption, also it says that air has a constant specific heat which is evaluated at room temperature or 25 degrees C. So air has constant specific heat which is evaluated at the room temperature, and that is 25 degrees C. All right, so the point of cold air standard assumption is the constant specific the specific heat of air during the process doesn't really change no matter what is the change in temperature. We assume that the specific heat is a constant number which is evaluated at 25 degrees C, because you know that the specific heat depends on temperature. If the temperature changes, the specific heat should also change. But whenever we are solving the problems under this assumption, then that specific heat is a constant number. Okay, so moving on, after these discussions, we had a couple of definitions about the reciprocating engine. So let's say if this is the cylinder, we have a bunch of discussion here or bunch of definition. So let's assume that this is our cylinder, and then let's say this is the location of the piston on top, and then this is the location of piston on the bottom, and the piston is relocating between these 2 points. So obviously when the piston is at this location, we have the smallest volume within the cylinder. So this location of the piston is called the top dead center. This location of the piston is called the bottom dead center. Right. So one stroke is the displacement from TDC and BDC. Okay. Top dead center, bottom dead center, stroke. The other definition we had was the compression ratio. Okay. So we have compression ratio. We show that with R. Okay. So we have three different R's. The first one is just R, and the other two R's, they have subscripts. So the compression ratio is the ratio of the maximum volume within the cylinder, which is basically the volume obtained when the piston is at BDC, over the minimum volume within the cylinder, and that's when the piston is TDC. Okay, so this is Vmax, and this is Tmax. I'm sorry, this is Vmean. This is Vmean. So if I want to show that with color, green is obviously Vmax, and red is Vmean. Okay, the other definition we had was about the mean effective pressure. Okay, so the mean effective pressure is the pressure that gives the same work between the minimum volume and the maximum volume displacement within the cylinder. The other classification that we had was the classification of the reciprocating engines. So we evaluate two classes of the reciprocating engines. In one class, which is the spark ignition engine, or SI, there is a spark that makes the combustion. Okay, so the combustion is initiated with a spark, as the name says. In other class of engine, which are the compression ignition, the combustion initiates when the mixture of air and fuel is compressed to a very high compression value, and there is no spark induced by us. In fact, the combustion starts at a very high pressure. So basically, these type of engines, they operate at a higher pressure compared to this type of engine. So basically, here the mixture of air and fuel is self-ignited as a result of compressing the mixture above the self-ignition temperature. Okay, so after these discussions, we discussed about the Otto cycle, the diesel cycle, and the Brayton cycle. So if I want to talk about the ideal Otto cycle, in the class, we started by discussing about the actual Otto cycle first, and then we discussed about the ideal one. So go over your notes. For now, for the review, I'm just doing the ideal Otto cycle. So you can imagine we have four different schematics. So let's say we have these four schematics, which are showing the cylinder. In the first schematic, the piston is going from state 1 to state 2. So that means we have our compression from 1 to 2 here, going from 1 to 2. Now, the piston is compressing the mixture of air and fuel, so obviously the pressure increases, right? Now, from 1 to 2, we assume that the entire cylinder is insulated, so there is no heat transfer from the cylinder to the surrounding and vice versa. So this hatch pattern, it shows the insulation, which means there is no heat transfer. Now, that was from piston going up from state 1 to state 2. Now, in the next schematic, the piston doesn't really move. It just stays at its location. Let's say it starts from state 2, and ends at state 3. So we have two different states but the location of the piston doesn't really change. But in fact, what changes here, or what happens here, is the heat addition. So this Q in, which according to the air standard assumption is representing our combustion. So instead of discussing about the chemistry of the combustion, we simply show that with a heat addition, which is Q in, right? And if you noticed here, our cylinder is not insulated, so you do not see these hatch patterns anymore. Now for the next schematic, the piston is providing some work, so it starts with state 3 and then goes down to state 4. Okay, so the piston is going down from 3 to 4, and that is exactly where we are receiving work that we need in the engine. Okay, so there is a mechanic boundary work operating here or happening here, which we can utilize that in our vehicles. But again, this schematic is similar to this schematic. That means there is no heat transfer from the cylinder to the surrounding or vice versa. That means we have this insulation around the cylinder. So insulation here, no insulation here. Okay, and finally, in the very last schematic, what happens is we have the exhaust stroke. Okay, so that means the piston doesn't really move. It starts from state 4, ends with state 1, which is, by the way, here, because the whole thing is operating in a cycle. And right now, again, the cylinder is not insulated, because if this is representing the exhaust, then according to the air standard assumption, we need to have a heat rejection, because we are representing we are replacing the exhaust process with the heat rejection process. So that means over here, there should be a heat going out, Q out. Okay, so heat addition here, heat rejection here. In both of these two, there is no insulation. Okay, so if I want to show these processes on a PV plot, so let's say from 1 to 2, obviously the pressure is increasing and the volume is decreasing. So let's say this is my 1 and this is my 2. The pressure is increasing as I go from 1 to 2. We go from this pressure to this pressure, but also the volume is decreasing. We go from this volume to this volume. And this is exactly what we have here. Now, from 2 to 3, the volume doesn't really change. So that means we should have a vertical line from 2 to 3. Now the question is the point 3 below point 2 or above point 2? Because the vertical line can go upward or downward. The thing is, because we have a heat addition, so the pressure is increasing. So that means my point 3 is above point 2, meaning that the pressure at point 3 is greater than the pressure at point 2. Now, from 3 to 4, the volume increases, the volume within the cylinder, increases. So we go to the right, and obviously the pressure drops. So this is what we have from 4 to 1. If you notice here, 4 and 1 give us the same volume within the cylinder. This is because the piston doesn't really move from 4 to 1. So that means point 4 and point 1 should be on the same volume, on the same horizontal axis, right? Because there is no displacement from 4 to 1. And finally, I can connect 4 to 1. So let's say this is 3 to 4 and this is 4 to 1. Now, I can show heat addition from 2 to 3. So let's say this is my Q in. I can show the heat rejection from 4 to 1. This is Q out. Now, because the discussion is about the ideal Otto cycle, then basically there is no friction or there is no irreversibility. Okay, because there is no irreversibility, then the process from 1 to 2 is going to be S constant. Because it is adiabatic, there is an insulation around the cylinder, and also it is reversible. So the combination of being reversible and adiabatic gives us S constant. Same thing applies to this schematic from 3 to 4. Because of the insulation and because of the fact that we do not have any irreversibility, then this is S constant. Okay, so by the way, because I had the definition of BDC and TDC, let me show you the BDC and TDC here. So BDC occurs when the volume is maximum. So this is my bottom dead center. And TDC occurs when the volume is minimum. This is top dead center. Okay? So this was a review about the Otto cycle. Now, I personally think that the PV diagram is extremely important because by looking at the PV diagram, we can easily develop Q in equation, Q out equation, and etc. For example, in Q in, there is no change in volume. So if you start with the conservation of energy as we did in the class, you should end up, for Q in, you should end up with difference of U's or internal energies between 3 and 2. The reason behind that is there is no change in volume, so there is no boundary work. Same thing applies here. So Q out is the difference in U's basically. Just for the sake of practice, let me do one of them. So let's say my goal is to obtain Q in, for instance. Q in and Q out are exactly the same. I'm just doing one of them. You can do the same concept for both of them. Although we did that in the class, so you should have that in your notes. But let's do it once again. So if I'm looking for Q in, then I need to focus on the process from 2 to 3. So that means this is going to be my system. Forget about the rest of the schematics. This is my system, right? In my system, I have two states, state 1 and state 2. And I need to focus on 2 to 3. Sorry about that. So I need to focus on this. In my system, I have two states, states 2 and 3. And between state 2 and state 3, although there is no movement in the piston, but between 2 and 3, this Qing applies, right? So if I start with COE, I would say energy going into the system minus energy leaving the system is equal to the change of the energy within the system. Okay, so this is the conservation of energy that I'm applying to my system. And once again, the system is this schematic, or the schematic that shows process from 2 to 3. Okay, I know that on the left hand side of COE, generally speaking, we have energy transfer by heat or work or by mass, because these are the dynamic forms of energy. On the right hand side, we have the change of energy in forms of internal energy, kinetic energy, and potential energy. Okay, but again, these notes are in general. It doesn't really mean that we have all of them in this particular system. We should evaluate that. So let's start with heat. If this is my system, during the process, which is from 2 to 3, there is a heat addition. So we do have this term on the left hand side, and that is Q in. So this is what we have. And because that the arrow goes into the system, then that is part of E in, or energy going into the system. It is not energy leaving the system, because in that case, the arrow would have been opposite direction. What about work? Do we have work here? The answer is no. There is no change in the location of the piston, so there is no boundary work. Don't forget that this work, it has different forms. It has electrical work, mechanical work, boundary work. If that is a boundary work, there should be a change in the boundary, or PDV, let's say. But the boundary doesn't really move, so no boundary work. No electrical work. You do not see any electrical resistance here. No mechanical work as well, because you do not see any paddle wheel, for instance. So we do not have work at all on the left hand side. What about mass? There is no mass going into this system during this process. Okay, during this process, the two valves that we typically have in the cylinder, they are both closed. So there is no energy going into the system by mass. So long story short, all we have on the left hand side of COE is Qing going into the cylinder. Let's do the right hand side. In the right hand side, we have difference of internal energy, kinetic energy, and potential energy. So let's start with potential energy. The potential energy of the system doesn't really change during this process. No one really relocates the engine from the third floor to the fifth floor to change its potential energy. So there is no change in potential energy. The same thing with kinetic energy. There is no change in the kinetic energy of the cylinder. Just note that on the right hand side we have delta, okay? That means we are looking at the change of, let's say, kinetic energy. Definitely when the engine is in the motion, we do have kinetic energy on the right hand side, but the point is that kinetic energy does not change. So long story short, P is 0, K is 0. And also about the internal energy, now here is the term that we have, because there is a heat addition and that basically changes the internal energy, and that will be, because that is delta, so it's going to be the internal energy at the final state minus internal energy at the initial state, U3 minus U2. Okay, so this is exactly the equation for Q in. Now here I made lots of discussion, so it's much easier if you want to do it really quick, but the same concept applies from 4 to 1. Now Q out is going to be U4 minus U1. Okay, so the reason that, so here you may ask, how come here it is final state minus initial state, but here it is the initial state minus final state? And that's a really good question if you ask that. The reason that Q out is U4 minus U1, so let me just do it really quick. So this time I'm trying to obtain Q out. So Cu is going to be energy going into the system minus energy leaving the system is equal to the change of energy within the system. And because I'm looking for Q out, this is my system. All right, now here's what. Again, on the left-hand side, I have heat, work, and mass. But, so you know that there is no work term, there is no mass term, as we discussed here. But we do have the heat term. But look at the direction of heat. That heat leaves the system. So that means that is part of E out. So that is negative Q out is equal to the change of internal energy. So U final minus U initial, and final is 1, initial is 4, because I'm focusing on this process, U1 minus U4. So that gives me Q out is equal to U4 minus U1, exactly what you have here. So the reason that here we have U4 minus U1 instead of U1 minus U4 as it should be, I mean, you may say, all right, this is final state minus initial state. So it should also be final state being U1 minus initial state being U4. No, that is not the case. Be careful that we do have a negative sign before the Q. So this is correct and this is correct. All right, so that was the review for the ideal Otto cycle. Okay, now I can also do the TS plot or TS diagram, and temperature is on the vertical axis, entropy S is on the horizontal axis. Okay, so from 1 to 2, once again, we had compression from 1 to 2. If you see here, from 1 to 2, we had the compression. So the temperature does change. But because here S is constant, my process on a TS diagram should be a vertical process. So let's say from 1 to 2, I have a vertical line. The temperature does increase because of the compression, but at the same time, entropy does not increase simply because the process is S constant. Now, from 2 to 3, again, the temperature increases, but this time from 2 to 3, entropy can change. It is not an S constant process from 2 to 3. Okay, so in fact, entropy increases from 2 to 3. So this is because of the heat addition. And then from 3 to 4, once again, I have an S constant process, but because of the expansion, the temperature drops. And finally, I have 4 to 1. Okay, so I can show the heat addition Q in and heat rejection Q out on this cycle. Okay, so, and here we had a bunch of equations. I'm not really rewriting the equations. Go through your notes, but there is one thing I want to review, and that is about the mean effective pressure. Okay, so I mentioned that the mean effective pressure is the pressure that gives the same work between the V mean and V max. Okay, so let's say if this is my PV plot, so again, I'm just doing the same thing here. So let's say this is our PV plot of the ideal Otto cycle. Okay, now the mean effective pressure is a pressure that gives us the same area. This area is W net, or the net work, right? And this is the V max and this is the V mean. So minimum volume within the cylinder, maximum volume within the cylinder. So the mean effective pressure is a pressure that gives us the same area between V mean and V max. So this line, or this value, is my mean effective pressure. So again, the mean effective pressure is kind of an average pressure that gives us the same net work with the ideal Otto cycle. Okay, so the next cycle I want to review is the ideal diesel cycle. Okay, and in ideal diesel cycle, the cycle kind of looks similar to the Otto cycle. The only difference is about the heat addition process. Okay, so in diesel engine, the heat addition or the combustion occurs at a constant pressure process. That is in contrast to the heat addition that we had in the Otto cycle. Here in the Otto cycle, the heat addition or Qin occurred in a constant volume process. The process from 2 to 3 is a constant volume process. But in diesel cycle, that is different. So in diesel cycle, if this is the pressure on the vertical axis and V volume on the horizontal axis, so from 1 to 2, we have the compression as before. Now, the heat addition occurs in a horizontal line or in a constant pressure process. And then from 3 to 4 and 4 to 1. Okay, so once again, the process from 1 to 2 is S constant or isentropic. The process from 3 to 4 is S constant or isentropic. The heat addition occurs from 2 to 3 in a constant pressure process, and heat rejection occurs from 4 to 1, Q out. Okay, so Q out here is exactly similar to Q out we had in Otto cycle, and that will be U4 minus U1. The question is about Q in. Can I say that Q in is also U3 minus U2? The answer is no, I cannot say that because this is different to what we had back in Otto cycle. Here, from 2 to 3, we have a change in volume. That change in volume causes boundary work. That boundary work on the left-hand side of the conservation of energy goes to the right-hand side and combines with U. So if I want to find Q in here, finding Q in, then I'll start with conservation of energy, and my system is basically the process from state 2 to state 3. So that is what I'm focusing on for Q in. Energy going into the system minus energy leaving the system is equal to the change of the energy within the system. Okay, so energy going into the system is in terms of heat addition or Q in. Okay, but I need to be careful because on the left hand side, I have heat, energy transfer by heat, energy transfer by work, and energy transfer by mass. All right. Now, this is the heat part, like Q in is the heat part. Regarding work, we do have work in this particular case, as I said. Okay. That work is not a mechanical work such as a paddle wheel, is not an electrical work such as an electrical resistance, but in fact, the work that we have from 2 to 3 is a boundary work, right? And that is because the volume is changing from 2 to 3. So the volume moves, the boundary moves, and because of that we have the boundary work. But the question is, what is the sign of that work? Is the work positive? Is that work part of E in? Or is that work negative and part of E out? This is really important. The answer is the work, the boundary work that we have from 2 to 3 is part of E out because we are not providing that work to the system. Q in is something that we provide and that is positive. But the work that we receive from 2 to 3 is something that the system gives us. All right? So that will be minus W boundary. Okay, so this is part of E out, which is equal to change of internal energy U3 minus U2. Now, this boundary work is PdV basically. Okay, so if I want to rewrite this equation, it's going to be Q in minus P2 change in volume V3 minus V2 is equal to U3 minus U2. Okay, now here I need to be consistent. I'm not really consistent in terms of units. Okay, the thing is, if this is volume, not the specific volume, so that means my total unit, the total unit is in kilojoules. So basically, if I want to be consistent with my previous notes, this should be Q in, capital Q I mean, and this should be uppercase U's. Okay, this is just to be the same, this is just to have the same unit for all different terms. Same thing here, this should be in uppercase Q and this should be in uppercase U's. Okay, once again, what is the reason behind that? The reason is this is volume, not the specific volume. So meter cube multiplied by the unit of pressure, which is kPa, gives me the unit of kilojoule. We did that in the previous videos. We walk you through the units. So if the entire thing here is in kilojoule, then I want to make sure that this is also kilojoule and that is also kilojoule. So unit wise, it gives me the unit of kJ. All right. So let's work on this equation here. So I would say Q in is equal to, what I'm going to do, I'm going to transfer this to the right hand side. And don't forget that P2 is also equal to P3. So I would say U2 plus P2V2 minus, U3 plus P3V3. All right. The reason that I said that is I'm transferring this to the right hand side. Okay, so I'm combining this term U3 term with P3V3 because P2 is equal to P3 and that is exactly what I have here. So this minus U2 plus P2V2. All right, so you know that the combination of U and PV is H enthalpy, the same thing here, H2, and all of them are in caps, right? Q in is equal to H3 minus H2, all of them in caps. So one thing I can do easily, I can divide both sides by mass, and that gives me Q in is equal to H3 minus H2. Okay, so this Q in is different from the Q in that we had back in the Otto cycle. In Otto cycle, our Q in was changing U's simply because the heat addition was done in a constant volume process, so there was no boundary work. But speaking of the diesel cycle, the heat addition occurs in a constant pressure process, so there is a boundary work because of changing volume. All right, so now here we have, you remember I said we have 3 R's. Now we have the second R here, and that is the cutoff ratio, RC. Okay, so RC is called the cutoff ratio, and that is this volume over this volume. So that is V3 over V2. If I want to do the TS plot for the diesel cycle, it doesn't really hurt if we do the TS plot as well. So the process from 1 to 2 was compression, so the temperature does increase, but here it says that S is constant. So from 1 to 2, I should have a nice vertical line. From 2 to 3, we had heat addition. Okay, so heat addition occurs from 2 to 3. So the temperature is increasing again from 2 to 3. From 3 to 4, I have another constant pressure, another constant S or constant entropy process. So let's say 3 to 4. And finally, from 4 to 1, we have the heat rejection. So this is our TS plot. So the point is the process from 2 to 3 is P constant. 4 to 1 is volume constant. Now, there are a couple of equations. Just go through your notes. I do not really see the point of rewriting all those equations. On the exam, you do have access to your textbook. Feel free to use the equations in the textbook. Feel free to use the equations in your notes, etc. So in this video, I'm just reviewing the core part of the discussion. So for the last part of the review, I would like to talk about the Brayton cycle. And I am reviewing the ideal Brayton cycle. So there are two applications for the Brayton cycle. One of them is in gas power plants, and the other one is in jet engine. So they are some of the applications of the Brayton cycle. So in ideal Brayton cycle, we have 4 components. So let's say this is the compressor, this is the heat exchanger, and this is the turbine. And here we have another heat exchanger. So let's say this is heat exchanger, this is another heat exchanger, this is our compressor, and this is the turbine. Okay, so state 1, state 2, 3, and 4. So in this heat exchanger, we have heat addition, and basically this heat exchanger represents the combustion chamber that we have. So this is Q in. This heat exchanger serves for Q out. So heat rejection in the cycle occurs here. And by the way, the turbine and the compressor are connected to each other with a shaft because this compressor needs some work input to be able to operate. Okay, so the PV diagram of this cycle looks like this: pressure, volume. From 1 to 2, obviously, this is the direction of the cycle, by the way. So from 1 to 2, as the working fluid, which is basically, let's say, air, because it should be a gas, as the working fluid passes through the compressor, its pressure increases. So from 1 to 2, we have compression and the pressure is increasing. From 2 to 3, in an ideal cycle, the pressure doesn't really drop, but instead we have a heat addition. So think about this process. The pressure doesn't drop, but we have a heat addition. So basically the volume increases from 2 to 3. And that is our Q in from 2 to 3. Now from 3 to 4, the high pressure gas is sent to the turbine, so its pressure drops and expansion occurs. So from 3 to 4, we have a drop in pressure and expansion occurs. And finally, from 4 to 1, we have the heat rejection. Okay? So from 2 to 3 is Q in, 4 to 1 is Q out. Now, how this cycle operates, that's the question. Now, it's pretty simple. Like, I think the combination of these two can explain easily, but the point is to compress the working fluid or air at a high pressure at that condition to add heat into that. So at point 3, we have high pressure, high energy working fluid, which is sent to the turbine. So that high pressure, high energy working fluid can rotate the blades in the turbine. Some part of that rotation is transferred to the compressor and some part of it is sent to the generator. Okay, so not all part of that rotation comes to sends back to the compressor. Then in that case, what's the point? We also want to get some rotation on the other side so we can put our generator to generate electricity, let's say. In order to be able to operate these in a cycle, we need to remove the heat and then do the process again. So that in that case, it operates in a cycle. Now, you remember I had 3 R's. So far we have done 2 R's. R, which is the compression ratio, RP, which is RC, which is the cutoff ratio, and here we have RP, which is the pressure ratio. Okay, RP is the pressure after the compressor to before the compressor, P2 to P1. Sometimes in problems, we consider the same ratio before the turbine to after the turbine. Okay, so this RP, which is the pressure ratio, can also be applied not only to the compressors but also to the turbine. So once again, the pressure ratio is the pressure after the compressor to pressure before the compressor, or the pressure before the turbine to pressure after the turbine. Okay, now I can also do the TS diagram for these, temperature, entropy. So from 1 to 2, in an ideal cycle, the entropy doesn't really change. So here I should mention that 1 to 2 is S constant. The same thing applies from 3 to 4. So 3 to 4 is also S constant. So that means the process from 1 to 2 is a vertical line. And from 2 to 3, we have the heat addition. From 3 to 4, another vertical line. And from 4 to 1, heat rejection. Okay. Q in, Q out. Okay, now here, by just looking at the PV plot, you should be able to tell the Q in equation and Q out equation. So for Q in, we have a change in volume. So because of that, Q in is going to be H3 minus H2. For Q out, we also have the change in volume. So there is a boundary work. So Q out is also H4 minus H1. So once again, there are lots of equations here. I don't really go through those equations. Go through your notes. I just try to do a review as we would do in a class, like maybe 15-20 minutes review, not more than that. So there are lots of discussion we did before the break. So definitely go through your notes for that exam. And I hope that this review can just refresh your mind on this chapter.